Okay, this may not seem like the most professional thing ever, but I'm probably going to post it to YouTube as a video entitled Helping My Nephew to Melt the Core of Mars. Yes, I'm using my shower stall as a whiteboard. Deal with it. Okay, things we need to know. And ask the things. A little more professional now. Things we need to know: total mass of the core of Mars, the approximate composition of the core of Mars, the heat of fusion for nickel and iron, which we're going to find out is the principal constituents of the core of Mars, which should allow us to calculate the total energy needed, and then we're going to convert that into some handy units like the total energy of an A-bomb, the total energy of a hydrogen bomb, and the total energy of the nuclear material in a typical fission reactor, which I'm going to go with, assuming that they keep about a year's supply on hand, because why not? These numbers should be pretty accurate, although I am definitely using some approximations, but we should be easily within an order of magnitude. I'm also going to skip over any uncertainties in the numbers and just kind of round things off to whatever seems good to me. There will also be some pausing while I look some things up. Okay, so NASA handily supplied the information that the mass of Mars core is approximately 24% of the mass of the planet. Now we just need to know the mass of the planet. Hang on. So the mass of the planet Mars is 6.4-ish. Hope my pen keeps working. Times 10 to the, 10 to the 23rd kilograms. So, hang on, I'll grab a calculator. So, if we take 24% of 6.4 times 10 to the 23rd, we're going to get, hang on, quick glance at the calculator here, just to prove I actually typed it in. We're going to get 1.54, call it. Yes, let's call it 1.5 times 10 to the 23rd kilograms. Sorry, I should have been pointing at the things I was writing. Looking up the composition of the core of Mars, there's not enormous agreement here, but we're going to go with the assumption that it is 90% iron and 10% nickel, which means that we have a mass of, really easy to calculate, 1.5 times 10 to the 22nd. Just reduce the exponent by 1. Kilograms of nickel, and the balance, hang on, we're going to call 1.35 times 10 to the 23rd kilograms of iron. Next, we need to look up the heat of fusion for nickel and the heat of fusion for iron, or the heat of melting, as some people now call it. So we get 293 kilojoules per kilogram for iron and 247. It's supposed to be a little j, or a little k rather. Kilojoules per kilogram for iron. Did I say iron? Anyway, 293 for nickel, 247 for iron. So that's going to give us 4.4 times 10 to the 24th kilojoules to melt all the iron. And 1.35 times 10 to the 23rd times 247 kilojoules per kilogram. Bringing us to a nice 3.3 times 10 to the 25th kilojoules for the iron. Adding those those two together. Give me a sec. And those two together, which is basically the same as, oops, sorry, 0.44 times 10 to the 25th here. Move the decimal spot over once. We get 3.74 times 10 to the 25th kilojoules.